morning, good afternoon, and good evening, everyone. Thank you for being here. My name is Yuechen Jiang, and I'm a first-year PhD student at the University of Manchester. Today, I'm excited to share our recent work. All that glitters is not gold, a benchmark for reference-free counterfactual financial misinformation detection, which has been accepted to the ACL 2026 main conference. I'd like to start with a simple but surprisingly difficult question. Can a model tell when a financial paragraph quietly changes? What you should believe? At first glance, this may sound like a standard misinformation detection problem. However, once we remove external evidence and require the model to rely solely on the paragraph itself, the challenge becomes fundamentally different. This is the core motivation behind RFC Bench. Let me begin with a real-world scenario. A paragraph appears in a trading terminal, a news feed, or even inside an AI-generated summary. Markets react within seconds, often before any verification is possible. Only later do analysts or fact-checkers step in. This means the critical moment is not after verification, but before it. As shown on this slide, financial decision-making often happens in a time-constrained setting, where retrieval-heavy fact-checking is simply not available. Existing benchmarks assume access to evidence, but real systems, real world, often do not. So, the key question becomes, should this paragraph even be trusted at the first glance? This exposes a key gap in existing benchmarks. Most datasets validate claims with evidence, but financial misinformation often works through subtle disclosed challenges rather than explicit false statement. A number might be changed slightly, a cultural explanation might be altered, or sentiment might be amplified. The paragraph remains fluent, but its meaning shifts. As highlighted here, RFC Bench focus on paragraph-level reasoning, no external evidence, and human-validated manipulation types. This positions our benchmark as a lower-level diagnosis, not whether a claim is true, but whether it should even be admitted into the reader's belief state. Before going into the dataset construction detail, let me give an intuition of what our dataset looks like. As shown in the figure, we start from an original financial paragraph and apply the minimal controlled edit. These edits are designed to preserve fluency and readability, while subtly changing the underlying meaning. For example, a directional shift can reserve an investment signal. A numerical change can alter the strength of evidence, and a cultural redirect can reshape the implied reasoning. The key point here is that these modifications are internally subtle. The text remains neutral, but what it suggests to the readers is different. This allows us to isolate a core challenge. Detecting misleading information from the paragraph itself without relying on obvious errors or external reference. Our goal is to ensure that the manipulation strengths we use are grounded in real-world financial misinformation rather than being artificially constructed. To do this, we start from existing survey on financial misinformation, which categorizes a wide range of misinformation types observed in practice. We then map these categories into 4 core manipulation types that capture the most common ways financial narratives are altered. An important design choice here is that each example in our dataset corresponds to a single manipulation type. While real-world financial misinformation is often more complex and may combine multiple strategies at once, we intentionally isolate these manipulation types to study them in a controlled way. The intuition is that if a model fails to detect a single well-defined manipulation in isolate, it is unlikely to succeed when multiple manipulations are combined in more realistic scenario. In this thing, our dataset provides lower bound diagonals. Building on this, we construct RFC Bench from real financial data. We collect over 1,400 Yahoo Finance articles and apply controlled perturbations. The key principle is simple: preserve surface fluence, but change what's the paragraph information. GPT 4.1 is being used to generate candidate rewrites, but human decide which example survives. This ensures that the datasets remain realistic while still being controlled. The generation pipeline constrained in two main stages. First, controlled LLM rewrite ensures minimal semantic changes while preserving fluency. Second, human quality assurance filter out ambiguous case through expert rewrite, agreement checking, and conflict resolution. These compiles allow us to produce reliable misinformation examples rather than noise data. To further ensure label quality, we will apply multi-layers of verification. This includes a special. After this process, we return 1,845 high-quality examples and a smaller set of hard cases. This ensures the benchmark is not ambiguous. If model falls, it's due to its reasoning difficulty, not label noise. We then define two kinds of tasks. Task 1 is reference-free detecting, where the model sees only a single paragraph and must decide whether it's manipulated. This setting reflects early-stage decision-making under uncertainty. Task 2 is comparative diagnosis, where the model sees both the original and perturbed paragraphs and must identify the manipulation type. As note here, the gap between those two tasks reveals what current models are missing. The result shows a consistent pattern. Task 1 remains near chance, with the best model reaching only around 53.6% accuracy. In contrast, Task 2 becomes highly reliable, reaching up to 97.7% accuracy. Few short promise helps only modest, and even domestic models like FMD Llama falls in Task 1. Because FMD Llama is also built upon the evidence verification base, this leads to a key insight. Model can explain after contrast, but they do not naturally doubt before contrast. We refer to this as an accommodation first failure mode. So, how about the human? To better understand this gap, we compare model performance with human performance under the same reference-free setting. A financial professional achieves 71.5% accuracy on task 1, significantly outperforming all evaluated models. This result is important, but it demonstrates that the task, while challenging, is clearly solvable without external evidence. In other words, the near-chance performance of LLM is not due to the inherent ambiguity in data, but reflects a limitation in current model capabilities. More important, this comparison highlights how humans approach the task differently rather than rely on surface patterns. Human experts draw on experience-driven, for example, sensitive to the rationality of direction, consistent with typical market behavior, and implicate expectation about how financial narratives should unfold. These forms of reasoning are often informal and difficult to articulate, but they enable humans to detect subtle inconsistencies even when the text remains fluent. This suggests that reference-free detection requires not just pattern recognition, but the ability from the challenge in eternal beliefs, something that current LLMs still struggling to do. We also investigate whether model performance is driven by superficial cues or generally reflects on reasoning ability. Few shot prompting provides only models improve overall, but its effects vary across model scala, as shown in the figure. Larger model benefit slightly from additional demonstrations, suggesting they can better utilize structured example to refine their decision boundaries. In contrast, smaller models do not consistently improve, and in some cases performance even degrades, indicating that simple adding more examples does not reliable enhance reasoning, especially when model capacity is limited. We further conduct a sensitivity check using a surface feature baseline, where the longest regression model relies only on shallow signals such as length, perturbation, and overlap. This baseline performs significantly worse than LLMs on task 2. When reference information is available, the result is important because it shows that models are not merely exploring superficial artifacts. Instead, they are generally capable of verifying semantic changes when explicit contract is provided. Taken together, these findings suggest that the performance gap between task 1 and task 2 is not due to surface-level shortcuts, but reflect a deeper limitation in reference-free reasoning. We then organized a shared test on the second workshop on misinformation detection in the era of LLMs to explore how far models can go without reference. As shown here, top systems achieved around 96% accuracy, far surpassing the baseline here. At first glance, this suggests that the problem may already be solved. But a closer examination reveals that these improves are largely driven by the introduced additional structure rather a fundamental breaking through in reference-free reasoning. Across different approaches, models are guided through mechanisms such as fine-tuned data argumentation, contrastive setups, or explicit reasoning, which effectively makes the task easier by providing external signals. This leads to a key insight. While performance improves significantly, the core challenge of reference-free misinformation detection remains unsolvable. Most systems still rely on learned perturbation patterns or distributed cues, and this erroneous degrades when fact with subtle, purely numerical, or previously unseen manipulations. In other words, current approaches improve detection by structuring the problem rather than enabling model to independently question a single fluent paragraph. To conclude, our results suggest that the core limitation of current LLM is not just in financial knowledge, but in how they form the update beliefs. When given a single paragraph, model tends to accept information at fact value rather than critical evaluation it. In contrast, human experts maintain a more stable internal belief state where new information is implicitly checked against the prior knowledge experience. This allows them to question statements that appear when they appear, even when the text itself is fluent and fluent. In other words, current LLM are better at explaining information when contrast is available, but they do not naturally doubt what they are given. Bridging this gap, by enabling model to reason under uncertainty and develop uh, is an important direction for future work. And that's all about my today's sharing.